Good evening, everyone. This is the problem solving session for the NPTEL course Fluidization Engineering. So, we are stepping into week 10 session. The course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. While this live session is handled by myself, Hankar Kartiga, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, every week from 6 p.m. to 8 p.m. we will be having we have been having the live session. So this is week 10. So let us step into the session. So the course layout is as given here. So basically this is just a repetitive of what I have been saying all the weeks, just to give some brief intro to whoever is joining as a new. So in the first week we saw what is fluidization, what are the advantages and disadvantages of fluidized bed, and what are all the applications. Fluidization is nothing but when we pass the fluid inside the packed bed at a sufficiently high velocity so that the particle starts to behave as a fluid. So this phenomenon is known as fluidization. So why do we go for fluidization? Fluidization ensures that there is a uniform heat transfer and enhanced mass transfer occurring inside the bed. So if that is the case, we can always go for fluidized beds rather than packed beds. So what are the advantages? Advantages, if we consider, there are few advantages, like the particles gets eroded and it loses its property. So and they may get carried away from the bed at some time, so we must be very conscious. This all leads to loss of particles. If it is a costly solids, this would be an issue. So it is a disadvantage. And what would be the applications? Fluidized bed is used in various industrial applications, like uh, in fluid catalytic cracking, biomass gasification, and so on. Like various reactions involve fluidized bed in their process. So in this was seen from the week 1 and 2, while in week 3 we saw about the characteristics of solids. So not all solids behave the same inside the fluidized bed. So we have 4 classification according to GELDAT. He classified the solids into 4 classes: GELDAT A, B, C and D. While A has medium sized particles, comparatively smaller sized particles, but they are very much used in fluidization because they do not cause bubbling. And FCC catalyst is an example for GELDAT A classification. Very smallest particles. This classification is given by GELDAT. He has classified them into 4 categories on the basis of the density difference between the density difference of the particle in the fluid phase and the particle diameters. So the very smallest one comes under GELDAT C particles. So GELDAT C particles, since they are very small, they are cohesive in nature. So it is very difficult to fluidize such particles. And next comes the GELDAT E. They have wide applications, but again it is having serious difficulties when we are dealing with fluidization of GELDAT A. Next comes the GELDAT B particles. These are nothing but widely used in fluidization because they have a controlled bubbling phase. So GELDAT B is larger than GELDAT A particles, and they are used in various applications. So next comes the GELDAT D particles. They are the largest particles. So what do? They cause spouting. They are easily carried away. So they are used in spouting fluidized bed. What do I mean by carried away? Like they would be moving in as a group. So they are used in spouted beds. So does depending on the characteristics of solids, the fluidization phenomena varies. Next is the flow pattern of fluidization system. So what did we learn in flow pattern? Like when depending on the fluid velocity that we are passing, the fluidization phenomena can be very different. Initially, before fluidizing, we call it as packed bed. Once at the minimum fluidization condition, where the fluid is particles are balanced by the incoming fluid, it is known as minimum fluidization, where the weight of the particles is balanced by the fluid and the drag and so on. Yeah. So this is minimum fluidization condition. So at after minimum fluidization only the particle starts to move. At minimum fluidization condition, the bed remains stable, so it is not moving. So after minimum fluidization, uh, the flow varies depending on the fluid medium as liquid or gas. So when the fluid medium is gas, we can observe smooth fluidization wherein we cannot see bubble formation. But if it is gas, we have bubble formation. So we have a series of things like the first one would be bubbling beds where bubble starts to form, and then we have slugging beds where the bubbles grow in size and they reach almost the size of the bed diameter. So the first one we call it as axial slugs, and it would be reaching the almost the size of the column, size of the bed. So I forgot the terminology for that slug, but it is comes under slugging bed, and then once they starts to break, they the particle circulation also happens at that moment. So once the particle starts to get thrown out, turbulent beds happen. So after turbulent bed, what happens is that once we pass the turbulent fluidization, we have pneumatic fluidization where carryover of solids do happen. So this is known as uh, turbulent fluidized beds and pneumatic fluidized beds. So once after this we have what did we see after that? We saw flow pattern of fluidization, flow pattern transition. So depending on the velocity and the diameter of the particle, velocity of the fluid and the diameter of the particles, we can classify them under and what condition it would come under. And also we studied about frictional pressure drop and its models to analyze. So after that it was about solid movement, mixing, segregation and staging. So this one is a content from this week's lecture. So we'll be dealing with what is how solid movement is happening inside the bed and segregation and mixing patterns inside the bed. So the frictional pressure drop and we would be dealing with how pressure drop happens inside the fluidized bed and across the distributor, and how the pressure drop influences the cost of the fluidized bed, because we need, depending on the pressure drop only, we need to recalculate everything. So that is there. After that we have gas distribution. So in gas distributors, we have small and large scale industries design of distribute. Yeah. So in gas distribution, we have different types of distributors like porous plate distributor, perforated plate distributor, nozzle type distributor, tear type distributor. So depending on the scale of the fluidized bed application, it can be anything. So mostly porous plate would not be used in industrial levels. And also we studied about the design of distributor, like nozzle placement, everything, like pores count and pressure drop, everything. So after that it was about bubbling fluidized bed. Bubbling fluidized bed itself accounts as a separate subject because there is so much to be learnt in bubbling fluidized bed. Gas dispersion and gas interchange in bubbling beds, mixing characteristics, everything. So after that it was about entrainment and elucidation from fluidized bed, where we saw once the particles uh, exits the terminal settling velocities of the particles, on the fluid exits the terminal settling velocity of the particles, it starts to get carry away the particles. So that is known as entrainment. So depending on this fine size, if few certain size range of particle is getting removed, that is known as elucidation. So that is again an important phenomena happening inside the fluidized beds. And in week 9 it was about attrition mechanism. Again attrition is looked into in this week lecture. And then it was about mass transfer phenomena, particle to gas mass transfer and its analysis by model in 2 and 3 phase system and modeling. And in heat transfer phenomena would be dealt in the last week with concern on design of fluidized bed reactors. So basically the books and references is that we have Cooney and Levenspil's Fluidization Engineering, which almost covers everything needed for this course. So and next is the Gidaspo's multiphase flow and fluidization, continuum and kinetic theory description. So when modeling the fluidized bed, it can be in two ways. One is accounting the solid phase as a Eulerian phase, and the other is solid phase as Lagrangian phase. In general, accounting solid phase as Lagrangian makes sense because the particles needs to be tracked individually. They have their own properties and motion. But if we are assuming the solids as a continuum phase, we need to account the motion of solids through another medium, that is kinetic theory of granular flow was obtained, which is similar to the kinetic theory of gases. And in 3 we have Giblaro's fluidization dynamics, and in 4 we have K Majumder's hydrodynamics and transport processes of inverse bubbling flow. So all these books and references would help you in understanding more in-depth and acquiring in-depth knowledge of the subject. So what we saw in last week was about entrainment and elucidation in fluidized beds. So as we discussed in few minutes back, what is entrainment? Entrainment is nothing but carryover of solids once the fluid exceeds the terminal settling velocity of the particles. So depending on the if the particles segregation is happening based on few size range, it is known as elucidation. So in addition to that, what else we saw in last week class? I think we saw about bubble model. I think it was about last to last class. Yeah, and in last class we saw about elucidation and elucidation rate, and also entrainment model, freeboard entrainment model by Cooney and Levenspiel, where if few people remember, there were 3 assumptions. The first one was assumption is that in a fluidized bed it is considered to be having 3 distinct phases in the freeboard region. The first is the gas stream plus the dispersed solids. The next one is the agglomerated solids coming from the bed, which is moving up, and the next one is the agglomerates, that is containing some wall layer of particles which is moving down. So we have 3 phases inside the freeboard region. And assumption 2 is that at any level in the freeboard, the rate of removal of fines from the agglomerate to form the dispersed phase, that is from phase 2 to phase 1 transition, is proportional to the volume fraction of agglomerate at that level. And at last we saw about the assumption was that when the upward moving agglomerate will be eventually reverse its direction and then fall back, right? So the frequency of that change from phase 2 to phase 3 is directly proportional to the agglomerate fraction of phase 2. So after that we solved so many problems last week, but I guess this week we do not have any problems. We are just having to go through the conceptual questions this week, and then yeah, it was about solid distribution inside the bed. So axial distribution, everything was studied last week, and an introduction to attrition mechanism was given also. So this week it is basically about attrition, solid mixing, solid segregation, everything. So first, before moving on to the this week's problem, we will just see what is attrition. So can anyone say what is attrition? I guess no one is there, so we have to manage ourselves. It's okay, someone would be watching this video in the future, so you people can also answer. So what is attrition? Attrition is the generation of fine particles by the acceleration and the collision near the tip of the gas jet promoted from the nozzle of gas distributor, that is attrition. Here we generate the final particles by means of collision and the acceleration of the particles near the gas jet. So consider this gas jet would be there. So the particles would be moving like this. Moving here. So because of the collision between the particles and the acceleration of the particles, if the larger particles is producing fines, that is stripping off of particles, we call it attrition. So it can occur by two ways. One is surface wear, because of the erosion of the surfaces and the fragmentation wherein the particle is getting broken down. And this week, in continuation with attrition, we studied communication theory. This one we would have dealt with in mechanical unit operation course itself. So in that course, in that aspect, we are dealing with three communication theories: Rittinger's theory, Kick's theory, and Bond's theory. So, and there were various tests to study the particles. In the communication process, and finally it was about the attrition models. So in attrition models we have three models. This again comes in the form of question also, so but just for giving you an introduction, we have three models. The first one is the jet induced model, and the next one is the bubble induced attrition model, and cyclone driven attrition model. So, and then it was about the breakage model inside the fluidized bed, and breakage rate, everything was studied. And finally we are coming into mixing and segregation. So it is very important to know the mixing and segregation behavior of the solids inside the bed. So the vertical movement of porous particles carry adsorbed reaction components up and down the bed. So this one lowers the conversion. So there is sometimes need for mixing, there is sometimes need for segregation. So depending on it, we should design the bed wisely. So there is again to study the mixing and segregation, we have various models. Like for vertical mixing we have a dispersion model, and then we also have a counter current circulation model. And also, like, with that we went into bed turnover time and residence time of the particles inside the bed. And then it was about multi-component like staging, where reactant components contacts a batch of solids. So depending on the staging we have various advantages, and then it is finally about multi-component thing. So that's it for the course in this syllabus in this week. So now we'll go on to the problems associated with this week. Let us just take a minute break because I'm just a little tired. It was a wholesome day today, so please don't mind. However, we have lots of time, right? We have 1.5 hours more, so we can cover it. So we'll start. Choose the correct expression for the overall attrition rate. RAO is equal to minus W by dWEL by dt. RA naught is equal to 1 by W by dWEL by dt. C RA naught is equal to minus 1 by dW by is into dWEL by dt. None of the above. So just think of the answer and give proper justification for the answer. We will discuss the answer in a minute. So the answer is option C. RA not is equal to minus 1 by W bed dWEL by dt. Can anyone say what W bed and WEL refers to? So W bed is the weight of the bed. That is the mass of the bed. So WEL is the mass of the elutriated fines. So this attrition, why do we need to study? We need to study because it affects the product quality. Because particle size distribution get affected, particle size, particle shape, particle surface area, everything changes because of attrition. So we need to be very careful when we are dealing with the attrition. So it is very much needed to study the attrition completely. So that is the case. Now we go on to question 2. In question 2, it is asked that attrition of the particles in the fluidized bed reactor is because of only surface wear, only fragmentation. Option C, both A and B. Options are right. Option D, none of the above. Similarly, think for a minute and then we will discuss the answer. If you have any interesting answers to say, you can put it in the chat box as of now, or if you are watching it later, you can put it in the comments, whichever is convenient for you guys. So I'll be happy to help you and we can have a discussion. So actually attrition of the particles in the fluidized bed is because of both surface wear as well as fragmentation. So this one we discussed previously also. In surface wear we have abrasion and erosion phenomena happening, because of which chipping or sliding and rolling, because of that the particle attrition happens. Whereas in fragmentation, large scale fracture or cracks in areas occurs in particles which in the regions where there is high level stress. So option A and B are correct. So moving on to question 3, we have which one of the following is true about Rittinger's theory? The energy required is proportional to the length of crack initiating breakage. Energy consumed is proportional to the area of new surfaces formed. Energy required to bring analogous changes is proportional to the volume of these bodies. None of the above. So just give the answer after a minute. So what does Kick's theory give? The energy required is proportional to the new surface uh, formed. The energy consumed is proportional to the new surface formed. So option B is the right answer. So then what would be the other statements? What are those statements from which theory? So the first one is energy required is proportional to the length of the crack initiating the breakage. So can anyone say what theory that statement is from? So that is from Bond's theory. And the last option C, it is mentioned that energy required is to bring analogous changes is proportional to the volume of those bodies. So that is from, sorry, this is from Bond's theory. The previous one was from Kick's. So energy required is proportional to the length of sorry. So the energy required is proportional to the length of crack initiating breakage is a statement from Bond's theory, while the energy required to bring analogous changes is proportional to the volume of these bodies is a statement from Kick's theory. So the right answer for Rittinger's theory is that energy consumed is proportional to the area of new surfaces formed. We'll go to question 4. In question 4 it is asked that choose the correct option. Rittinger's theory E is equal to C into 1 by x2 plus 1 by x1. Bond's theory Q E is equal to 2 times of C into 1 by square root of x2 minus 1 by square root of x1. And then we have Kick's theory, option R, E is equal to minus ln of x2 by x1. S is equal to, option S, E is equal to C into 1 by x2 minus 1 by x1. So we have option A where 1 is P, 2 is Q, 3 is R. And option B, 1 is S, 2 is R, 3 is Q. Option C, we have 1 is Q, 2 is S, 3 is R. Option D, 1 is S, 2 is Q, 3 is R. So match it and then we'll discuss the answer after a minute. So actually from Rittinger's theory, what we have is he is equal to c times 1 by x2 minus 1 by x1. So the right option is option S. So 1 is for S. So we have either B or D. And then for Kick's theory, Bond's theory, we have E is equal to 2 times C into 1 by x2 root square root of x2 minus 1 by square root of x1. So for Bond's theory, we have Q. So it is B and D. So option 2 we have Q. So option 3 we have Kick's theory. For Kick's theory, we have E is equal to minus ln of x2 by x1. So answer is option R. So we have S, Q and R. So this is not right. This is wrong. Again this is wrong. So answer is option D. S, Q and R. So we'll go to question 5. In question 5 it is asked that choose the correct options. So option 1 bubble induced attrition. For that we have function of jet penetration length. Option 2 we have cyclone driven attrition and jet induced attrition. So option Q we have due to the forces exerted by the cyclone on particles and due to the high velocity interparticle collisions, due to the low velocity interparticle collisions. So we have 4 options. The first one is option 1, R for 1, Q for 2, P for 3. Or B we have S for 1, R for 2, Q for 3. And C we have S for 1, Q for 2, P for 3. D we have Q for 1, S for 2, R for 3. Discuss the answer after a minute. So the bubble induced attrition is because of the low velocity interparticle collisions. So and cyclone driven attrition is because of the cyclones due to the force exerted by the cyclone on the particles. And we have jet induced attrition, which is because of the gas distribution from the jet penetration length. Because of the jet penetration length. This one, it affects the number of nozzle holes, nozzle diameter, Q, V, volume, rho G, everything it is affecting. So what do we have? We have 3. The first one is bubble induced attrition, cyclone induced attrition, jet induced attrition. For jet induced attrition, it is because of the function of jet penetration length. For bubble induced attrition, we have it is because of the due to the low velocity interparticle collisions. Cyclone driven attrition is because of the due to the forces exerted by the cyclone on the particle. So on matching all these we have S, Q, P. Which option it is matching is RQP false, SRP false, SQP is the right answer, that is option C is the right answer. Again option D is wrong. S, Q and P is the right answer, option C. We will go to question 6. In question 6 it is asked that choose the correct option regarding the breakage probability of material during attrition. The breakage probability of the material is a strong function of cyclone inlet gas velocity, particle concentration and its size, material specific constant, all of the above. So as we all know, take a minute and discuss the answer, because all these are theory questions covered in this week. So there is nothing new to be explained. If you have understood the concepts, you would be able to answer. So just think and recollect the concepts and we can discuss. So the right answer is all the above. So the breakage probability of the material is a strong function of cyclone inlet gas velocity, particle concentration and its size, and the material specific constant. So the change in the particle size distribution of the material undergoing the stress is what defines breakage model. So in that, cyclone inlet gas velocity, solids load and the diameter of the particle and the material specific constant, everything plays a role. So solids concentration and its size. So all the above is the right answer, option D. So we'll go to question 7. In question 7 it is asked that the dispersion model reasonably represents the vertical mixing in a tall beds in which rather small scale mixing is taking place. Select the correct expression for the dispersion model. The dispersion model reasonably represents the vertical mixing in tall beds in which rather small scale mixing is taking place. Select the correct expression for the dispersion model. Dou CTP by dou T is equal to dSV into dou square CTP by dou Z square plus US into dou CTP by dou Z. Or option B, it is dou CTP by dou T is equal to dSV dou square CTP by dou Z square minus US dou square CTP by dou Z square. Option C, it is dou CTP by dou T is equal to dou square CTP by dou Z square into dSV minus US into dou CTP by dou Z. Or option D, dou CTP by dou T is equal to US into dou square CTP by dou Z square plus dSV into dou CTP by dou Z. So just think and then we'll discuss. So the answer to this question is option C, I think so. Yeah. Dou C Tp by dou T is equal to dSV into dou square C Tp by dou Z square minus US dou C Tp by dou Z. So this is for vertical mixing in beds which rather small scale mixing is taking place. So DSV here is the vertical mixing, so it is V. Dispersion model due to vertical mixing. CTP is the concentration of the tagged particle. So dou CTP by dou T is equal to DSV dou square CTP by dou Z square minus US into dou CTP by dou Z. So S here is the solid's velocity and Z is the vertical, because of vertical mixing it denotes the height difference, or else height. We'll go to question 8. I think before that we can take a break. We'll take a break and then we'll come back. However, we have crossed almost half of the session, so we'll take a break and then we'll start the session. For a completely mixed stirred tank reactor, the residence time distribution can be expressed by the following expression, where Tr denotes the mean residence time of the particles. R of T is equal to Tr exponential of minus T by Tr. R of T is equal to 1 by Tr into exponential of T by Tr. R of T is equal to 1 by Tr ln of minus T by Tr. D, option D, R of T is equal to 1 by Tr into exponential of minus T by Tr. So, find out the answer, we'll discuss it in a minute. So, it is 1 by T R exponential of minus T by Tr. So, answer is option D. R of T is equal to 1 by Tr exponential of minus T by Tr is the right answer. Now, we will go to question 9. In question 9, it is asked that the residence time distribution for a system with n stages of fluidized bed reactors of equal size can be calculated as R of T is equal to 1 by 1 minus n factorial into Ti into 1 by Ti into exponential of T by Ti. R of T is equal to 1 by 1 minus n factorial Ti into 1 by Ti into exponential of minus T by Ti. Option C, R of T is equal to 1 by 1 plus n factorial into Ti into 1 by Ti into exponential of minus T by Ti. R of T is equal to 1 by 1 minus n factorial into Ti square into 1 by Ti into exponential of minus T by Ti. Find out the answer, we'll discuss the answer. So the answer is R of t is equal to 1 by 1 minus n factorial into Ti divided, I mean that comes in the division Ti into 1 by Ti into exponential of minus t by Ti. So the thing is, we can see this one remains the same, 1 by Ti into exponential of minus t by Ti. So the remaining terms only varies depending on the n number of stages. So 1 minus n factorial also comes in picture. So the answer is option B. We'll go to question 10. In question 10, it is asked that the solid mixing index is defined as the ratio of mass fraction of jetsam in the top portion of the bed to the jetsam mass portion in a perfectly mixed bed. Select the correct answer regarding the solid mixing index. M is equal to 1 indicates complete mixing. M is 0 indicating complete segregation. Option A and B are right. M is equal to 0 indicates complete mixing. It's a very simple question, so I would suggest you take out a piece of paper and a pen and write all the options which you think is correct, and then mark those so that it would be helpful for you in the future. So answer is option C. Both options A and B are correct. Since M is the mixing index, if M is 1, it indicates complete mixing, whereas M is equal to 0 indicates complete segregation. So option C, that is both A and B are right, is the correct answer. We'll go to question 11. In question 11, it is asked that segregation index S defines the intensity of the particle separation in the bed. Choose the correct statement regarding the segregation index where SF denotes the flotsam mass fraction in a perfectly mixed bed. S is equal to 1 by XF denotes complete segregation. S is equal to 1 denotes state of perfect mixing. Options A and B are right, none of the above. So in this case as well, both the options A and B are right. So S is equal to 1 by XF denotes the complete segregation, and S is equal to 1 denotes complete mixing. So XSF denotes fraction of flotsam. So what is flotsam is that the particle that floats. We have two particles in the binary fluid mixture in the fluidized bed. So one is jetsam, one is flotsam. So if it is perfect segregation, we have x is equal to s is equal to 1 by xf. S is equal to 1 denotes complete mixing. So segregation index S is defined by XSF top in the top region, by XSF in the completely fluidized bed. Completely mixed bed. So S is equal to 1 by XF denotes a perfect segregation or complete segregation, and S is equal to 1 denotes a perfect mixing. So we'll go to question 12. In question 12, it is asked that the changing composition with the bed level of two spherical particles, species differing in both diameter and density, can be determined using volume average density rho p. The volume average density can be represented by the following expression. Rho p is equal to C1 rho p1 plus C2 rho p2 by C1 plus C2. Rho p1 plus rho p2, or in option B, it is rho p is equal to C1 rho p1 plus C2 rho p2 by C1 plus C2. Option C, it is C1 rho p2 plus C2 rho p1 by C1 plus C1, or option D, it is C1 rho p1 plus C1 rho p2 plus C2 rho p1 plus C1 rho p2 plus divided by C1 plus C1. So option 1 is the right answer. Option A. Option B. Yeah, it is should be divided by C1 plus C2. C1 rho P1 plus C2 rho P2 is equal to divided by C1 plus C2 is the right answer. So here we are using changing composition with the bed level for two spherical particle species differing in both diameter and density can be determined using volume average density. So for that purpose, we are using concentration and the density and multiplying it and dividing it by the total concentration. So yeah, we'll go to question 13. In question 13, it is mentioned that choose the correct option for bed suspension density, where rho p, rho, epsilon s, epsilon l denote the particle density, liquid density, volume fraction of small particles, volume fraction of large particles respectively. In the absence of smaller particles, rho b s, in the absence of larger particles, and options P, rho bs is equal to rho p into 1 minus epsilon s plus rho s epsilon s, rho b l is equal to rho p into 1 minus epsilon l plus rho epsilon l. Option R, rho b l is equal to rho p into 1 minus epsilon l plus rho p into epsilon l. Option S, it is rho b s is equal to rho p into 1 minus epsilon s plus rho p into epsilon s. One is R and Q, S and R, Q and P, P and Q. So think and then we will discuss. So actually, in the absence of smaller particles, density would be rho BL equal to uh, rho P into 1 minus epsilon L plus rho into epsilon L. So Q, and I think it is P. Q and P. Option C. So yeah, in the absence of smaller particles, we would be having only larger particles and the fluid. So we have rho P into 1 minus epsilon L. That is rho P, the particle fraction 1 minus epsilon L gives the amount of particle fraction plus rho into epsilon L. Similarly, rho P into 1 minus epsilon L plus rho into epsilon S gives the one for the smaller particles, that is in the absence of larger particles. So just think and analyze the question completely, because here it is given absence of smaller particles and absence of larger particles, not the other way around. So you might get confused at some point, so please be careful while reading the questions. So we'll have question 14 now. In question 14, as per Richardson and Zaki, the voidages for the monocomponent bed is represented by epsilon S is equal to epsilon L into ds by dl power 3 minus m by mn. Uh, epsilon S is equal to epsilon L into dl by ds into 3 minus m by mn. Similarly, epsilon S is equal to epsilon L into dl by ds into mn by power mn by 3 minus n, 3 minus m, or 3 plus m by mn to the whole power of, whole power for the term dl by ds into epsilon L. So think for a minute, we will analyze it. So the answer is option, I guess it is option B. Yeah, epsilon S is equal to epsilon L into dl by ds 3 minus m by mn. So this is according to Richardson and Zaki's model. The voidage for the monocomponent bed is represented by this. Oh God. We'll go to question 15. In question 15, choose the wrong answer regarding attrition. Spray dried crystals are allergic to attrition. For the same type of materials, but of different sizes, fractional loss due to attrition is larger for smaller particles. Smaller particles are more difficult to break than larger ones. Option D, none of the above. So think an answer. We will discuss the answer in a minute. So the right answer is option D, none of the above, because spray-dried crystals are really allergic to attrition, and similarly for same type of particles of different sizes, the fractional loss due to attrition is larger for smaller particles, and smaller particles are more difficult to break than larger ones. So option D, none of the above is the right answer. So these are all the questions for this week. If you have any doubts, please ask or else we'll take a 5 minutes break and then we'll just give a quick recap of the week's lesson and we'll end this week. Yeah. This is just a 5 minutes break. If not, we'll come back again after that. So yeah, we'll have a quick recap and then we'll close this week's session. So basically, in today's week, what we saw was about mixing and segregation with focus on attrition and attrition models. Attrition is a continuation from last week's class. So in attrition, what is attrition? Attrition is the generation of fine particles because of the accelerate when the particles collide and accelerate near the tip of the gas jet. So overall attrition rate REO is given by minus 1 by W by dW bed by dt or minus 1 by W bed dW EL by dt. That is the mass of elutriated fines. So why do we need to study attrition? Attrition because it affects the product quality in terms of particle size distribution, size, shape, surface area, everything. So what are the mechanisms in which attrition happens? It can either happen through surface wear or fragmentation. In surface wear, it can happen through either abrasion or erosion, where chipping of the surface or sliding or rolling of the surface occurs. And the next is the fragmentation. In fragmentation, large scale fractures or cracks occurs in areas with high level stress. And then it was about comminution theory. In comminution theory, it is three theories are given. One is Rittinger's theory, Kick's theory, and Bond's theory. In Rittinger's theory, it is given that energy consumed is directly proportional to the new surface formed. So, and in Kick's theory, it is given by energy consumed is directly proportional to the volume of bodies of geometrically similar bodies. Or in Bond's theory, it is energy consumed is directly proportional to the length of crack which is initiating the breakage. And general equation is given by dE is equal to minus C dx by xn. So this n factor varies for different theories. For example, it is 1 for Kick's theory and 2 for Rittinger's theory and 3 by 2 for Bond's theory. And x is the fineness of the material. So based on this, we get equations for Rittinger's theory, Kick's theory, and Bond's theory. And there are various experimental techniques to study the comminution or the load bearing capacity of the material. And next is the why do attrition, how do attrition occur, and what are all the models to study that. The first is the jet induced attrition, second is bubble induced attrition, and third is cyclone driven attrition model. In jet induced attrition model, it is given by the volume above the gas distributor, that is the jet penetration length. So it is affecting the factors affecting here are nozzle diameter, number of nozzle holes, volumetric flow rate of the fluid, velocity of the fluid, and the velocity inside the orifice, and the density of the gas. And the next is the bubble induced attrition model, where it is because of the low velocity interparticle collisions. And the third is cyclone driven attrition model, where cyclones force on particles. The force of particles from cyclone is causing attrition. And then we saw about breakage model, wherein it is affected due to gas inlet inside the cyclone and solid load and solid size and material specific constant. It is nothing but the change in the particle size distribution of the brittle material which is undergoing stress, mechanical stress. So and then it was about surface breakage rate model, where there were many models like Fan's Schweitzer models, Arena 1983 model, surface reaction model, which is nothing but the reaction rate is proportional to the surface area and selectivity. And then finally we saw about the mixing and segregation. In mixing and segregation, the vertical movement of the particles carry adsorbed reactant components up and down the bed. Because of this, the conversion and the selectivity is reduced. And there are various models like row model, fan and Naigium, everything which explains how the mixing occurs, because the bubble carries some amount of solids and then those solids are left behind by the wake. So it is either due to bubble drift or bubble wake shedding, which causes mixing inside the bed. So this is given by vertical mixing or horizontal mixing, and the models expressing these are dispersion model and counter-current circulation model. So, and then it was about bed turnover time. Solid circulation is due to bubble wake and bubble drift. So, average time needed for the particles in bed, that is bed to be circulated, is known as bed turnover time. So, actually, uh, the turnover time should be less than the residence time of the particles inside the bed. So, in segregation occurs, we have, if it is a binary bed, we have jetsam and flotsam particles. Jetsam is nothing but those that sink. Flotsam is those particles that floats to the top. It may be due to density difference or size difference. If it is due to density difference, the segregation occurs readily. If it is due to size difference, it does not occur so. And depending on the velocity, the segregation rate is influenced. So we have mixing index and segregation index. If m is equal to 1, it means complete mixing. M is equal to 0 denotes complete segregation. Whereas S is equal to 1 by SF denotes complete segregation, perfect segregation. S is equal to 1 denotes complete mixing. And we have staging where reactant gas contacts the batch of solids, that is known as vertical staging. So, and then in the course content, we also saw about the multi-component fluidization and how to calculate the minimum fluidization for those cases. So this is this week's content. So in the next week, again we will meet at the same time from Friday 6 p.m. to 8 p.m. So where we will be dealing with, I think it is week 11 next week. So we will be dealing with heat transfer or mass transfer, I guess. Yeah, mass transfer phenomena we will be dealing with in the next week. So finally, if you have any questions, please ask now. I'll wait 5 more minutes. If there is no doubts, we'll close the session or else we'll clear the doubts. Yeah, thank you. If you want to leave, you can leave. Well, thank you guys for attending this week's session. We'll meet again next week. If you have any doubts, you can always post it in the comments or in the forum of the NPTEL course. So I thank everyone for attending this week. Mm, yeah, thank you guys. Thank you. And one more thing. Uh, Today's session, I knew it was kind of boring because I'm not feeling very well today. Apart from this, I'm finding no one is joining the session. If there is any fault from my side, please feel free to say so that I can improve in the next week session. Or else, if you are expecting, or if your expectations are something else different, please feel free to say that too. And apart from that, if you are having any issues in the problem solving session in terms of NPTEL, other than my sessions, you can always give your feedbacks, it would be accounted. So that's what I wanted to say. So please don't hesitate to say anything. Your valuable feedbacks would be heard. So take your time and respond. Uh, yes, thank you.